Now in this video, we are going to revise the formulas that are coming under these three topics: shear stress, bending stress, and principal stress from strength of materials. Now let's get into it. Starting with shear stress, we shall see the general and basic formula to find the shear stress for any section. So that will be calculated by using this formula: tau is equal to SAY bar by IB. And S is nothing but the shear force acting at any section, and AY bar is the moment of area above Y about neutral axis, and Y bar is the distance of center of area that will be calculated from the neutral axis, and I is the moment of inertia about neutral axis, and small b is the width of section at a distance y from neutral axis. So here you can refer in this diagram what is y bar actually. Y bar is the distance from the neutral axis to the center of the shaded portion. So this is the y bar distance, and A is the area of the shaded region or the region that we require to calculate shear stress, and AY bar is the moment of area about Y about neutral axis, and I we know moment of inertia, and B is the width of section. Now we shall see a particular section. For that particular section, how to calculate shear stress how it is varying. For rectangular section, shear stress will be calculated by using this general formula: tau is equal to S by 2i into d square by 4 minus y square. Here y is nothing but the distance calculated from the neutral axis to the uh, bottom of the shaded region. So that is the y distance, and d we know depth of the beam, and S is the shear force, and I is the moment of inertia. This is the actual shear stress variation diagram of a typical rectangular section. Here you can see at the neutral axis, tau max, that is shear stress will be maximum at the neutral axis, and the average shear stress lies here, that is at a distance d by 2 root 3 from neutral axis. And tau max is equal to 1.5 times tau average, or 3 by 2 times the tau average, and tau max lies at neutral axis. And there is some other thing called shear force at upper and lower third. So upper and lower third portion, what will be the shear force, and at middle third, what will be the shear force. So shear force at upper and lower third shall be 7s by 27, and at middle third it shall be 13s by 27. This is a basic observation regarding calculation of shear force at the upper and middle third sections. And these three formulas are basic things regarding rectangular section. And now we shall move on to triangular section. So for triangular section, how shear stress varies. This is also parabolic, and shear stress formula is like this: 12s divided by bh cube into hx minus x squared. So what is x here? X is the distance measured from the apex of the triangle to the bottom portion of the shaded region. So if you want to calculate the shear stress in this shaded region, so what is the bottom portion of it? Up to that uh, distance measured is called as x, and h is the height of the triangular section. So tau is equal to 12s by bh cube into hx minus x square is the general shear stress distribution formula for a typical triangular section. And this is also parabolic and similar to the rectangular section. And for tau max, it shall be 3 by 2 into tau average. And what is basically a tau average? Tau average is nothing but shear force by uh, the cross sectional area. Here what is cross sectional area? Half into b into h. And in case of rectangular section, it shall be b into d. Here b into h, half into b into h is the cross sectional area. So tau max is equal to 3 by 2 into tau average. And at neutral axis, what will be the shear stress? 4 by 3 into tau average. So this is the basic shear stress distribution in case of triangular section. So tau max will be at h by 2, and tau average will be at tau average will be at neutral axis. So at neutral axis, 4 by 3 into tau average, or tau average is equal to 3 by 4 into tau neutral axis. Now let's move on to circular section. For circular section, Shear stress varies by this formula. Shear stress distribution goes here 4s by 3 pi r power 4 into r square by y square. So what is r? Radius of the circular section, and this is also parabolic in nature. Shear stress variation is in parabolic in nature, and equation is like this: 4s by 3 pi r power 4 r square minus y square. So what is y? The distance calculated from the neutral axis to the bottom portion of the shadowed region. And here tau max is equal to 4 by 3 into tau average, and tau average and tau max lies at the neutral axis, and tau average lies uh, somewhere at the half of the semicircular portion, that is r by 2. At r by 2 tau average lies. So these are the basic and important formulas regarding circular section shear stress distribution. Now let's see some special cases in other sections, how to calculate the shear stress and what is the variation. In case of diamond section, that is a square section having its diagonals, one of its diagonals horizontal and one of its diagonals vertical, how shear stress varies? Shear stress varies like this. So at 3 by 8 times the h is the total height of the section. At 3 by 8 times the h, tau max lies. So what is the tau max value? Nothing but 9 by 8 times tau average. What is tau average? Simply shear force by cross sectional area of this section. So tau max is equal to 9 by 8 into tau average. This is a special case regarding a diamond section. And tau at neutral axis shall be the tau at average. So what is the neutral axis here? Neutral axis lies at the central region, and at this region what is the shear stress? That is nothing but tau average. And for slit section, circular slit, what is the tau max? Tau max is equal to twice that of tau average. So these are some special sections to calculate the tau max and tau average. Now we will move on to bending stress. So in bending stress, we follow the pure bending theory. So what actually is the pure bending? Pure bending is nothing but dm by dx. That is, so at any section, shear force shall be 0. That is called as pure bending. Shear force shall be 0. And pure bending equation goes like this: m by I is equal to sigma by y equal to E by R. What is m? M is bending moment, I is moment of inertia, sigma is bending stress, y is the centroidal distance, E is equal to Young's modulus of elasticity, and R is the radius of curvature, and 1 by R is the curvature. So R is like this, radius of curvature. So a beam bending like this having a curvature radius of R, curvature radius of R, that is given here in this diagram. You can clearly see. So R is the radius of curvature, and there is another thing called section modulus. So in case a beam having higher section modulus, then that beam has the strongest section. Higher section modulus relates to the strength of a beam. So Z is equal to I by Y max. So section modulus is nothing but the ratio of moment of inertia to the maximum centroidal distance of that beam section. Now we shall see more formulas on the basis of shape of the section, that is rectangular, triangle, like that. Before moving to that, we shall see the strongest section. So what will be the strongest rectangular section that can be made out from a circular wooden log having diameter d? So x is equal to d by root 3. What is x here? The width of the strongest rectangular section. That is nothing but x is equal to d by root 3. And y is the depth of the strongest rectangular section. That is nothing but y is equal to root of 2 by 3 d. So this is the strongest section that can be made out from a circular wooden log, so that uh, bending strength shall be more. Accordingly, this section modulus shall be more. And in case of diamond section, we have to cut out the top and bottom portion by a by 9, so that this section has higher section modulus before cutting it. So higher section modulus can be obtained by cutting the top and bottom portion by a by 9. So this is the a by 9. And what actually is the a? A is the side of the square section. This is the A. A is the side of the square section. And in case of circular beam, we have to cut the top and bottom portion by 0.011d so that we can get a stronger section modulus. For circular beam, we have to cut top and bottom portion by 0.011d. So these are some basic and important formulas regarding the strongest sections based upon section modulus Z. Now we shall see other important things regarding bending stress. We can calculate force on partial area by using bending stress concept. So P is equal to sigma max divided by Y max into AY bar. So what is sigma max? Maximum bending stress. And what is Y max? Y max is the maximum centroidal distance. And AY bar is the moment of area of the shaded region, or the region that about which we have to calculate the force, on which we have to calculate the force. So that moment of area of that region is given by A into Y bar. So how to calculate Y bar? Y bar is nothing but the distance measured from the neutral axis to the center of the shaded region. This is the Y bar distance. And this is the Y max distance. So upon calculating these values, we can get the force on that partial area. And a beam, if loaded with axial forces, then how to calculate bending stress? Bending stress can be calculated using summation of direct stress and bending stress due to direct force, that is plus or minus P by A, and plus or minus bending My by I. How bending will be there? Whether it can be a transverse load, UDL or point load, or it can be self weight or anything else. Because of transverse load, bending will be there. And due to some axial loaded condition, we have to add this term, that is plus or minus P by A. Accordingly, whether it is compression or tension, accordingly we have to change the sign. And if we want a beam having uniform strength across every cross sections, we have to modify that beam accordingly based upon breadth or based upon depth. And if we want to calculate using depth or breadth value, we can go like this. For a breadth section, that is Bx, that is breadth at x section, Bx is given by this formula, 3w divided by sigma d square into x, 3w by sigma d square into x. And in case we have to calculate in terms of depth value, changing depth at every section, we can go by this formula, dx is equal to root of 3w by b sigma into root x. X is the distance from the distance of the section from the right end or left end, anything else. And these two formulas are applicable only for a simply supported beam subjected to central point load, not any other case. Only when simply supported beam subjected to central point load, we can apply these two formulas in order to get a beam of uniform strength. Now we shall see formulas under principal stress. First we shall see one plane condition, 1D only. So for one plane condition, that is normal stress acting over only one plane, that is in x-axis only or in y-axis only. Then how to calculate normal stress in a particular plane? So for this plane, we have to calculate normal stress, that is denoted by sigma n. Sigma n is equal to sigma x cos squared theta. And at that plane, what is the shear stress? Sigma x by 2 into sine 2 theta. And what is the resultant stress? Resultant principal stress? Resultant normal stress, sigma r is equal to root of summation of the squares of normal stress and tau is the shear stress. So this is a one plane condition. Now we shall see stress acting on two plane perpendicularly. Two mutually perpendicular planes. In this condition, what is the principal stress and shear stresses? Here, no external shear stress is acting, that is, no external shear stress is acting. So that's why sigma x is equal to major principal stress, that is denoted by sigma 1, and sigma y is equal to minor principal stress, that is denoted by sigma 2. And how to calculate normal stresses? sigma n, that is, so in this plane, in x-axis what is the sigma n value, and y-axis what is sigma n dash value. Sigma n is given by sigma 1 plus sigma 2 by 2 plus sigma 1 minus sigma 2 by 2 into cos 2 theta. Theta is nothing but angle made by the plane with a vertical here. This is the theta. And what is sigma n dash value? The same, but just change the sign over here, minus. And how to calculate shear stress? Using this formula, tau is equal to minus sigma 1 minus sigma 2 by 2 sine 2 theta. Just change the sign with minus, and here sine 2 theta. And at 45 degree or 135 degree, there will be maximum shear stress. How to calculate that? Sigma 1 minus sigma 2 by 2. At 45 degree means sine 90 degree. So sine 90 is 1. So that's why just sigma 1 minus sigma 2 by 2. And at 45 degree cos 90 is 0. So this term gets cancelled out. Only this term is there. So that's why sigma n is equal to sigma n dash equal to sigma 1 plus 2 by 2. So these are some basic things. And now let's see the angle of obliquity. Beta is the angle of obliquity, and tan beta is given by tau max divided by normal stress, and that shall be equal to sigma 1 minus sigma 2 by sigma 1 plus sigma 2. And how to calculate beta max? Sin beta max equal to the same thing, sigma 1 minus sigma 2 divided by sigma 1 plus sigma 2. So these are the formulas that are coming under this scenario, this case, two mutually perpendicular planes, stress acting on two mutually perpendicular planes. Now we shall see along with shear stress. So here normal stress also there and shear stress is also there, both type of stress acting on perpendicular planes. In this case, how we are calculating the principal stress and normal stresses? So sigma x dash is equal to the same thing, but we have to add this term plus tau xy sine 2 theta. And for sigma y bar, we have to add this term minus tau xy sine 2 theta. And for tau xy dash, we have to add this plus tau xy cos 2 theta. The same formula is there, but we have to add shear component. And at tau xy bar, tau xy dash is equal to 0, there will be no shear stress. That is at no shear stress, which is the plane? That is nothing but the principal plane. So angle of inclination of that principal plane shall be found by using this formula. Tan 2 theta p is equal to 2 tau x by sigma x minus sigma y. At 0 shear stress and at that plane, that is nothing but the principal plane, how is the inclination? Tan 2 theta be equal to 2 tau x by sigma x minus sigma y. And the principal stresses can be found by using this formula. Major principal stress is sigma 1 and minor is sigma 2. That is nothing but sigma x plus sigma y by 2 plus or minus root of sigma x minus y the whole by 2 the whole square plus tau x by the whole square whole root. By using this relation, we can find the major principal stress and minor principal stress, then normal stress and shear stresses acting on perpendicular planes. And now let's see some special case. So pure shear is a special case. In that case, no normal stress is acting, only pure shear, only shear is acting. You can see in this diagram, only shear is there, no normal stresses are present. So this is one type of special case. So for this case, at a plane at a theta degree, what is the normal stress? Sigma x dash is equal to tau xy sine 2 theta, and sigma y bar is equal to minus tau xy sine 2 theta. And tau xy dash, that is in that plane, what is the shear stress? That shall be tau xy cos 2 theta. And at that under 0 shear stress, what will be the plane? That is nothing but theta equal to 45 degree. At 45 degree, 0 shear stress will be there. And what is the principal stresses? Sigma 1, that is major principal stresses, plus tau xy, and minor principal stress sigma 2 is minus tau xy. So this is the pure shear condition. And now we shall see the Mohr circle. Here two things are there. One is the radius and another one is center of Mohr circle. Mohr circle is always symmetrical to x-axis. So that's why center is at sigma x plus sigma y by 2 comma 0 0 only. And in this Mohr circle we can note the points from the origin to the last point is the sigma 1, that is major principal stress, and sigma 2 is lies here, and at the center what is the value, just average it, sigma x plus y by 2. And the radius of Mohr circle gives the tau max. Radius of Mohr circle gives the tau max, and that is nothing but root of sigma x minus sigma y by 2 the whole square plus tau xy square the whole root. So that gives the value of tau max, that is maximum shear stress. By using Mohr circle also we can calculate the maximum shear stress by simply knowing the radius of Mohr circle. Now we shall see some other important formulas regarding principal stress. There is one concept called stress invariant. That is nothing but sum of the normal stresses is equal to constant sigma n plus sigma n dash, that will be equal to sigma x plus sigma y, and that also be equal to sum of the principal stresses. All these sums equal to a constant. This is called stress invariant. And until now we studied only based on principal stresses. What if we want to calculate in terms of principal strains? Just replace this value sigma 1 into epsilon 1, that is principal strain, that is major principal strain, sigma 2 into epsilon 2, minor principal strain, and tau xy bar is stress, and this is phi xy bar is the strain, and tau xy bar has to be replaced by this phi xy by 2. So this is how we have to calculate in terms of principal strains. And the diameter of Mohr's strain circle. So we have already seen the Mohr's stress circle. In that, radius of Mohr's stress circle gives the maximum shear stress. But in terms of strain circle, the diameter of Mohr's strain circle gives the maximum shear strain. So that varies, diameter and radius. And if we know the values of principal strains and also the properties of metals, we can calculate the corresponding principal stress values by using this relation. Sigma 1 is equal to E by 1 minus nu square, nu is Poisson's ratio, into epsilon 1 plus nu epsilon 2. And if you want to calculate sigma 2, just interchange the values, epsilon 2, epsilon 5. So this is the basic and important formulas regarding principal stresses. So we have learned the formulas from shear stress, principal stress, and bending stress. Subscribe the channel and stay tuned to get more videos like this. Thank you for watching.